In the previous lecture, I had forgot to say that you can expand the determinant along any row or any column. So it's important. You can expand the determinant along any row or column. Basically because determinant of A is same as minus 1 times determinant of Eij times A that we had seen. So that will take care of any row. And if I want to look at any column, then we know the determinant of A is same as determinant of A transpose. All right, fine. So I would like you to understand this part yourself. So what we know is the determinant of A, if I write A is an n cross n matrix, then this is equal to J is equal to 1 to n. If I write Aij here, then there will be minus 1 to the power I plus j will come, fine. And then there will be determinant of from A, remove the ith row and the jth column. This is what I'm supposed to look at, fine. So what we do is that to understand it better, there's a notion of what is called a cofactor matrix, cofactor of A. This is supposed to be the Cij, capital C for you, and is again it was an n cross n matrix. So this is also an n cross n matrix. And Cij, if I want to look at Cij, Cij is coming from here, which is minus 1 to the power I plus j, determinant of A of ith row and jth row, remove it, and look at this. So whatever extra term I have here in other than I just keep it. So this term and this term together, they come and give you this part, Cij. Is that okay? Minus 1 to the power I plus j, determinant of A and I and j, and this is true for every I and j. Is all right? So for 1 less than equal to ij less than equal to n. So you can compute all of them. All right, so this is called the cofactor matrix. Cofactor of A. Fine. So there is another notion what is called the adjugate of A. So in general, we know it as adjugate of A, but earlier we used to know it in the classical time, it was called as adjoint of A. So this is a classical language, and this is what we learn in our school. But adjoint in mathematics or at higher level is something else. It's related with a star and things like that. A star. We'll not get into it. We'll say adjugate or sometimes just adj, or by mistake because we're used to that part, adjoint will come. But adjoint is different. All right. Fine. So adjugate of A is nothing but look at the cofactor matrix of A and take a transpose of that. Is that okay? Or which is same as cofactor of A transpose. Fine. So whatever way you want to understand, you need to understand it. Fine. So what we have done here is that if I look at determinant of A here, determinant of A is nothing but j is equal to 1 to n Aij into Cij. All right. So what we are saying here is that we are looking at AI1, AI2, AIN, and then we are multiplying it with, just look at 1C, 2C, so Ij, I1 and I1. Fine, this is 1, Ci2, Cin. All right. So I should not write small c, there may be some confusion. So let me write capital C itself, Cin. Fine. Is that okay? So this is the way you have to understand. Now, so what we are doing it is that here I have got ith row here and Ci1, Ci2, Cin. Fine. Since I'm looking at Ci1, I have removed the ith row. So the element AI1, AI2, AIN does not appear in any of the Cij's. All right. Fine. So in place of I, if I look at say AK1, AK2, AKN, and then I want to look at what is Ci1, Ci2, Cin. I would like you to understand that if k is not equal to I, then in Ci1, if I look at, I just remove the ith row. So ith row, so AI1, AI2, AIN is lost. 1 is here, so first column is lost. So, but this element will be there sitting inside this part. All right, why it will be sitting inside? Because I'm looking at when I remove the ith row, kth row is not lost. Kth row is still there. So what will happen is that this whole thing corresponds to a matrix in which the ith row and the kth row are same, and therefore this determinant will be 0. All right, because we have seen that if the two rows are same, then the determinant is 0. All right, so this is nothing but summation j is equal to 1 to n akj cij here, k is not equal to I, so this will be equal to some determinant of a matrix B, which will be 0. What is B? B is a matrix in which the ith row of A is replaced by the kth row, and all other rows are same, and all other rows of B are same as the corresponding rows of A. All right, so there is no change except for the ith one. Ith row has been put as the kth row, that's all. So which is the ith row of A is replaced by the kth row, that's all. All right, fine. So this turns out to be 0. So what happens is that when I want to compute something, these are useful to you. So I have looked at in terms of rows. You can also do in terms of columns because of determinant of A transpose is same as determinant of A and things like that, fine. So let's try to understand it through an example. What I'm talking about, example. So be careful, I may do some mistake, or I may have done some mistake in my calculation itself in my notes. I do not know. So 2, 3, 1, 1, 2, 4. I want to compute adjoint of A. So let me first compute what is cofactor of A. So cofactor of A is going to be a 3 cross 3 matrix. Fine. So first I have to remove the first row and the first column. So it is 3 into 4 is 12. 12 minus 2 is 10. So I'll get this 10 here. Please be careful because I'm looking at minus 1 to the power 1 plus 1. All right. Now I have to remove the second here. 1, 2 into. So I remove this. I get 8 minus 1, which is 7. It will come with minus 7. Why will come with minus 7? Basically because I am looking at minus 1 to the power 1 plus 2. Fine. If I remove the first one and the third column, we will get 2, 3, 1, 3, which is 4 minus 3 is 1. And it will remain 1 basically because minus 1 to the power 1 plus 3 is that. Fine. If I look at 2 here now, 8 minus 6 is 2. So it will be minus 2 here because minus 1 to the power 2 plus 1. If I look at this, it is 4 minus 3 is 1. So it will remain as 1. Fine. This part will be 2 minus 2. 2 minus 2, which will be 0 here. If I look at this part, it will be 2 minus 9, that is 7. So minus 7 here. Fine. Then I look at this part, it will be this part goes off, this part goes off. 1 minus 6. 1 minus 6 is minus 5. So minus 5 here. So it should be 5 because minus 1 to the power 2 plus 3 into minus 5. So it is minus minus plus. So it is 5 itself. That's correct. Fine. And the last one will be 3 minus 4, which is minus 1 here. Fine. So this is what I get cofactor as this. And therefore adjoint of A will be equal to transpose of this. So it will be 10 minus 7, 1, minus 2, 1, 0, minus 7, 5, and 1. Fine. So just be careful, that's all. And verify that whether I've done the things correctly or not. Fine. So let us compute A times adjoint of A. Fine. So I would like you to see that 1, 2, 3, 2, 3, 1, 1, 2, 4 times 10 minus 2 minus 7, minus 7, 1, 5, and 1, 0, 1. I hope it is correct. Or there's a minus 1 here. See, I do a mistake here. I have done a mistake from the notes. So this is this. So check out that this is nothing but determinant of A, 0, 0, 0, determinant of A, 0, 0, 0, determinant of A, which is same as determinant of A times identity matrix. All right, I3. Is that okay? So just verify it yourself. And the same thing will be true because of the transpose part. It will be same as adjoint of A into determinant of A. Fine. So try that out yourself. It's not difficult to understand it. Fine. And therefore what happens is that so as a corollary of this idea, if determinant of A is not 0, then what we see is that then A times 1 upon determinant of A into adjoint of A is identity, which is same as 1 over determinant of A into adjoint of A times determinant times A. So this is also A here, and this is also A here. So as a mistake as usual, this is this, and this implies if determinant of A is not equal to 0, implies A inverse is equal to 1 over determinant of A into adjugate of A or adjoint of A, whatever you want to say. But be careful because it is not the adjoint which is nowadays talked about. All right, so you have to be careful. Fine. So keep track of this for yourself. Now a theorem, and then the Cramer's rule theorem, which I'm not proving it, but you should know. Let A belonging to Mn of C, then the following statements are equivalent, then the following statements are equivalent. In the notes, I have just written a few, but there are quite a few which you should take care of. A is invertible. Because in the earlier lectures, I don't remember to have said them, but maybe I'll put them in the assignments. I have not yet made them, so maybe I'll do that. The linear system Ax is equal to B has a unique solution for every B. Maybe I should put it differently. So A is invertible. That I already know that A is product of invertible matrix and things like that. So 3. The sequence is slightly wrong, I think. All right. The RREF of A is identity for determinant of A is non-zero. Fine. 5. The homogeneous system Ax is equal to 0 has only the trivial solution. Unique solution will imply that it's trivial solution. So from here, 2 I should have written. So maybe I should have written this as, so let me just change these numbers, I think. So I don't remember exactly what the sequence is, but I would like you to know that 1, this should be 2, say 3. You can prove the equivalence, all right, 4, 5. You can have 6 as the linear system Ax is equal to B has a solution for every B. Sorry, for every B. So if you look at 5 and 6, there I'm talking in terms of unique solution. Here I'm saying that there is a solution, all right? Fine, so you can do that. And that will imply that A is invertible. So I should have also written that at some stage that another one here, maybe say 2 prime or 2, whatever it is, that A is product of elementary matrices. Fine. So this we have already seen. So you can relate all of them. There are quite a few. Similar things are there. We'll come across afterwards also when you look at what is called the rank nullity theorem, and we'll relate all these ideas. All right. Now we look at what is called the Cramer's rule. I'll not give the proof, but the proof directly comes from looking at RREF of A's identity. All right. So it comes directly from there. So let A be a non-similar matrix. Fine. Did I say that? Yeah, determinant of A is not zero. All right. So let A be a non-similar matrix. So this implies that A is an invertible matrix. So I know what the inverse is, what the things are. All right. Fine. Then the unique solution of the linear system system. Ax is equal to b is given by xj is equal to determinant of aj upon determinant of a, where x is nothing but your x1, x2, xn transpose the unknowns, all right, and aj is the matrix obtained from A by replacing the jth column by B. So rest of the entries remain the same. There is a change there only. All right, fine. So this is important. So what we are saying is that if I look at AJ, AJ is supposed to have the first column as it is, no change. Second column will remain as it is. Till J minus 1th column, it will remain the same. At this stage, there will be a B here. That B, the RHS, will come. And then you will have again the J plus 1th column, and so on till the nth column. All right, this is what the matrix AJ is. Fine, and true for 1 less than equal to J less than equal to n as such. And J minus 1 will be 0, means there is nothing there in the beginning. All right, so this is what it is. So I'd like you already know it, so I'll not get into that part. But the idea of the proof will be, if I want to look at the proof, what I know is that A is determinant of A not equal to 0 implies A is invertible. Fine. Now A is invertible will imply that there exists a matrix P so that P times A is identity. Fine. So that's what I'm going to use as such. So if I look at P times, so this part tells me that P times the first column will be equal to E1, P times the second column, all right, will be E2, and so on till P times the last column will be equal to En. All right, this is what it is. Look at this part. All right, fine. So what we are doing here is that we are just using the idea of this P, which will come again and again. And therefore, if you look at the determinant here, below and above, I can multiply by P and then proceed. All right, so what I'm saying is that Xj is determinant of Aj, determinant of A. So I can just multiply by determinant of P on both the sides. Determinant of P into determinant of A, I can write like this, which is same as determinant of Paj by determinant of Pa. Now determinant of Pa is 1. So this is same as determinant of P times Aj. And which you want to look at, so it is same as determinant of this matrix. P times A1 is E1, then it is E2 here. It will be PB in the jth column, and then so on En here. All right, and therefore this determinant will be nothing but this is a diagonal matrix with PB of J here. All right, fine. PB of J is a column, so you have to look at the jth part. Fine, and therefore you get that answer. Fine, is that okay? So no, I should not have written this. I should have just written here this, because it is PB as a column and I'm looking at the jth entry of that column. Jth entry in the jth column. All right, fine. Because I'm looking at xj, jth entry of PB. And this is what xj is. Fine. So that's the way you have to understand it. Very simple. Just have a look at my notes. You will be able to get these answers. Fine. I'm not solving it for the particular example. Just try that out yourself. Fine. So that's all in this lecture. And we would like to look at things. In some of the things what I've left is assignments. So just try that out. Look at the assignments clearly. Because in the next class, I'm going to go to what are called vector spaces. All right. System of linear equation is over. Whatever is left out, we'll look at it in assignments. Thank you.